Okay, in this video, we're going to continue on with the logistic regression model. Specifically, we're going to look at doing some inference for this model, so some hypothesis tests and confidence intervals. So just remember from last time that the logistic regression is used to build a model where we have at least one explanatory variable, but the response variable is binary. In this chapter, we're just looking at a special case where we have one explanatory variable. But in Chapter 10, we'll look at the case where we have multiple explanatory variables. But in every situation, the response variable is always binary. So remember from last time, we saw that there's two versions of the logistic regression model. One is the log odds model, and that's this. Okay, and there's a log odds has this linear relationship where x is the explanatory variable. So this model can be used to predict the log odds of success. If we exponentiate both sides, this will give us, and then solve for pi, this gives us the probability form. So this will allow us to estimate the probability of success. Remember that everything we're doing, we're just going to always use the natural log base e. Okay, so last time we looked at this med school GPA data set that looked at predicting whether or not a student would get into med school based on their GPA. So we're going to continue with that today. So remember back from earlier in the semester with linear regression, simple linear, and multiple linear regression, we had three types of hypothesis tests. We had a t-test to see if the slope for a particular explanatory variable differed from 0. So that was used to check the effectiveness of one variable at a time in the model. The other extreme was to have an ANOVA F test, and we used that to check the general overall fit of the model. And then finally, we looked at something in between those two. The nested F test allowed us to test a subset of predictors. So we're going to do something similar in this section and in Chapter 10. So the test will be different, but the ideas will be the same. Okay, so the first test to test just to check whether or not a particular variable is effective in the model is something known as Wald's test. And so let's think of, so the hypothesis is that the beta 1 is 0 versus beta 1 does not equal 0. And the test statistic should look familiar to what we've seen earlier. I just caught that this is a typo. Beta 1 should have a hat on it in both cases. Okay, so let's think about the med school data. Pi is the probability of being accepted into med school. And so the model that we were using is looking at estimating the logistic curve, so the log odds of being accepted. And our explanatory variable we were using before was GPA. I'm going to suggest we use GPA multiplied by 10 just to make the units easier to interpret when we interpret the slope. So what I suggest you do to start off is to open up that data set and create a new variable called GPA 10 and use a calculator to multiply all the GPAs by 10. Okay, so let's go ahead and think about fitting this model with the logistic curve. So if you go to regression, the usual place we were last time, binary logistic regression, and then fit the binary logistic model, if we select those options, okay, this is going to bring us to the screen. Now we just want to be a little bit careful here. So when this screen will pop up. You're going to choose a response variable to be acceptance, and your continuous predictor will be the GPA 10 variable. Okay, before you go any further, you want to make sure that you select options, and then you want to actually, I believe it was under, not options, excuse me, under click results instead. And that will pull up this screen. And change this drop down. The default is simple tables. We want to choose expanded tables. Okay, so because otherwise you won't get your z-test statistic, it won't show up, so choose that. Okay, so if you do that, you're going to get this set of output. Okay, so let's look at interpreting this. So just a couple of things. Your z-test statistic turns out to be right here, 3.45. And you can see up here that to get that z-test statistic, you take beta 1 hat and divide by its standard error. So if you were to take 0.545, that's your beta 1 hat, and divide by its standard error, 0.158, you'd get that z-test statistic. Again, if you don't do expanded tables, you won't see this. You'll get just like this part of the output. Okay, a couple of things to notice. You'll also see this as part of the standard output. The chi-squared value is exactly z squared. Okay, and so the p-values, and no surprise, are the same. You get 0.001. So that's a small p-value. So this suggests that there's a strong evidence between a log linear relationship between med school acceptance and the variable GPA 10. In other words, that this GPA seems to be an important variable in the model. Okay, so now we might want to do some estimating of that slope coefficient beta 1. So this formula hopefully looks familiar. To estimate beta 1, we'll use the point estimate, beta 1 hat, and add and subtract to it a margin of error, where the margin of error involves standard error and z star. Remember, z star is just your confidence, it corresponds to your confidence level. So if we want to be 95% confident, then z star would of course be 1.96. Okay, so put 0.545 in for beta 1 hat, put 0.158 in for the standard error, and 1.96 for the z star. And if you do that, you'll get your confidence interval to estimate beta 1 to be 0.236, comma 0.855. So this is estimating beta 1. Okay, so just remember that this is our model that we're using. And if you look at this model, it's linear. And what the slope coefficient here with this beta 1 is doing is it's saying for each unit increase in GPA 10, we're estimating the change in log odds. So if we want to put this in something meaningful, describing the rate of change in terms of log odds isn't that meaningful. So remember what we do, we want to undo this log process. So if you undo the log, so take e to both of these values, you end up getting a confidence interval that looks like this, 1.27 up to 2.36 or 35. In any case, this is this interval here. Okay. Also notice that the odds ratio, remember, is just e to the beta 1 hat, the estimate for it. So if you take e raised to 0.545, you get this number. Okay, and that's what's in parentheses here. So this is your odds ratio, estimate in this case. Okay, so how are we going to interpret then this interval? So we're saying for every tenth of a unit increase in GPA, because we were using the variable GPA 10, so for every tenth of a unit increase in GPA, we're expecting that the odds of acceptance go up by a factor of 1.27 and roughly 2.4. So it doesn't matter if your GPA goes from 2.0 to 2.1 or 2.8 to 2.9 or 3.5 to 3.6. What we expect is your odds of getting into med school is going to increase by a factor somewhere between 1.2 and 2.4. Just keep in mind that this is estimating the odds, not the probability of acceptance. Okay, so now we'll move and think about what would we do if we want to do a general test to look at the overall fit of the model. Again, we're not going to see any difference here right now, but when we get into multiple linear regression, we will. So if you remember back the ANOVA F-test, we were measuring the overall fit of the linear model. And it was based on seeing how the sum of the squares of the error terms changed when we went from a model that had no explanatory variable in it to putting in an explanatory variable. What we were doing is, what the process looked at is to minimize the sum of the square of the residuals. And Minitab did that for us. With logistic regression, we're going to minimize a quantity that looks like this. It's strange looking. It's -2 times log L, and L stands for the likelihood. So I'd like you to read page 439, which gives a little bit of insight into this. But the important idea is it's going to lead us to a new test statistic. So we no longer have an F-test statistic. We have something called the G-test statistic. And from that test statistic, we can get a p-value. And the p-value is based on using the chi-square distribution with 1 degree of freedom. Minitab will compute the G-test statistic for us. And let me show you how to do that. So start off in the usual place by going to regression, binary logistic regression, etc. And let's take a look at this now. So what you want to do here, that'll give this pop-up window once you do that. We'll put acceptance in the response still, GPA 10 as a continuous predictor, but now you want to select options. Okay, and when you do that, this pop-up window comes up. And what you want to do for your test for the ANOVA table, the walled is the default. You want to select likelihood ratio test. That's what we're using now. Okay, and just a couple of other things here. So once you do that and hit OK, you'll get this output in part, this ANOVA table. Okay, so this G-test statistic is right here. So you don't have to compute it by hand. It's 18.95, and the corresponding p-value is approximately 0. So this tells us that the success of getting into med school does depend on GPA. Okay, that this variable was useful in this model. Overall effectiveness of the model is good. Okay, just a couple of things. This likelihood ratio test is sometimes called a G-test or a drop in deviance test. They all mean the same thing. Okay, the last thing we're going to look at in this section looks at what do you do when you have a binary predictor. The example we just did, the predictor was GPA, which was a continuous random variable. So what do you do now when your explanatory variable is binary? So let's look at this example, and it's an example you should have read about. It was in the earlier part of chapter 9. But it had to do with a study that investigated whether a handheld device that sends magnetic pulses into the head might be an effective treatment for migraine headaches. And so people were either given the treatment, TMS, or a placebo, and they were asked to report whether or not they were pain-free 2 hours later. So from the TMS group, you can see that 39 out of the 100 were pain-free. So the probability of success was 39%. And for the placebo group, the probability of success was 22%, to give you a difference of 17%. And the odds ratio was computed earlier in the text for this example, and it was 2.27. So the odds of being pain-free are more than twice as high for the TMS group. Okay, so we want to see if these results are statistically significant, so we'll have to run a hypothesis test. So to do this, you have to convert, in Minitab, you have to convert this two-way table into something that looks like this. So in the first column, put in the groups, and we have 2 groups, TMS and placebo, and then the second group was whether or not they were effective. So we've got these 4 scenarios. In 2 situations, we're in the TMS group, and but in one case, the treatment is successful or effective, and then it's not effective. So that's where these 2 rows are coming in. And then we have the placebo groups, successful and not successful, or effective, not effective, and their counts. So turn the two-way table into a table in Minitab like this before you go run the regression. Okay. So if you do that, go to the usual place, regression, binary logistic regression, et cetera, et cetera. And then in the pop-up window, you'll get, this screen. So you want to, in the response, you want to put in effective, and then count in frequency, and the categorical predictor. Remember, group is categorical, so it goes down in this lower box. So do that, and you can hit OK. Okay, so, and in part what you'll get is this output. You should still have the expanded tables selected from earlier, and if not, you'll need to go back under results and make sure that shows it so that you get the z-test statistic. Okay, also I should say that we're just doing a Wald's test right now, so you can select Wald's test back in the results section. Okay, so a couple of things. Notice that in our model here, this coefficient is positive, okay? All right, so the subject is more likely to be pain-free with TMS than the treatment using the placebo. Okay. And what this tells us then is that remember what we were doing here is looking at predicting log odds of success. And X is the TMS, whether or not it's an indicator function, 1 or 0. If the treatment was used, or 0 for the placebo. Okay, so what this is saying then, this log odds, remember that's what the beta 1 is, as beta 1 changes from placebo to TMS, we're looking at how much the log odds changes by. And our estimate then is 0.818 here. Okay. So if we undo the log process, we'll get e to the 0.818 is equal to 2.27. And that's our odds ratio, or estimated odds ratio. Okay. So again, we're saying that with the odds of being pain-free is more than 2 times that when the treatment's used as opposed to the placebo. So that's just based on the sample data, but we want to know, are these results statistically significant? And what you can see from the ANOVA table, so really what we're running here, folks, right, is that the null hypothesis is beta 1 is 0 versus the alternative beta 1 is not 0. And with the Wald test, you get a z-test statistic of 2.58 with a p-value of 0.01. So there's strong evidence of association between the treatment and the response. And moreover, this was a randomized experiment that was done, so we can determine cause and effect, that the treatment does seem to have an effect on pain. Okay, just a couple of other things. From this, we can also do a confidence interval. Remember, these are bounds that estimate beta 1, so if you take e to both sides of it, you end up getting this confidence interval 1.22, 4.22. And I noticed, even though we had in the mini tab with this version, that the odds ratio is selected, for some reason the output is not giving the odds ratio and the corresponding confidence interval. So, but it's easy enough to do. Remember, to get the estimate for the odds ratio, just take e to the beta 1. And to get the corresponding confidence interval, just take the confidence interval of beta 1 and take e to both numbers. So this is your confidence interval for the odds ratio. All right, so what we can say is we're 95% confident that TMS increases the odds of being pain-free as compared to the placebo by a factor of between 1.22 and 4.22. Okay, so that wraps up Chapter 9. In Chapter 10, we'll look at adding more predictor variables into our logistic regression model.